In this example, we will interpret scatterplots. Earlier in the statistics course, we looked at scatterplots when we were learning about graphs for quantitative data. So recall that a scatterplot compares two quantitative variables on the x and y axes. And we've talked about association with scatterplots. When the slope is increasing, we say the scatterplot has a positive association. And when the overall slope is decreasing, we say the scatterplot has a negative association. So down here we have three scatterplots that differ in the direction of the association. And so we can describe the association as positive, negative, or neither. And then we have three different descriptions that could match these possible scatterplots. So we are going to match the descriptions to the scatterplots and explain our reasoning. So the first scatterplot has a negative association as the x-axis increases, the y-axis decreases. So as we read through the three possibilities, the best fit seems to be the second choice, where x is the amount of sodium in milligrams per serving in some sort of superfood, and y is a consumer reports health ratings for 10 brands of tomato soup. So if a soup has more sodium, this seems possible that it would have a lower consumer reports health rating because we know higher sodium is probably less healthy. And so that's the note we've put here for our reasoning. Higher sodium soups are going to be less healthy. The second scatter plot seems to have no real association. If we tried to fit a line through here, it would probably just be a flat line through the middle without a slope. So the third choice below seems to be the best fit, where x is the price in dollars, and then y is the sodium in milligrams per serving for 10 different brands of vegetable soup. So it makes sense that there's probably not a relationship between the price and the amount of sodium in the soup. The price is probably associated with whether it's a name brand or generic or organic or something else. Our scatter plot 3 here has a positive slope, and we think that that's the best match for the first description, where x is the city miles per gallon for a car or truck, and y is the highway miles per gallon for 10 cars or trucks. And so it makes sense that a car with lower city miles per gallon probably also gets lower highways miles per gallon. It's not a very efficient car. And then a car like a hybrid that gets higher city miles per gallon probably also gets higher highway miles per gallon. So to recap, scatterplot 1 shows a negative association where the x values increase, the y values decrease. Scatterplot 2 shows no association. We see the points dip down and then back up again. And scatterplot 3 shows a positive association. As the x values increase, the y values also increase. And then we're just noting the association between city miles per gallon and highway miles per gallon for the sample of cars is positive. That was our third graph. The association between sodium in a serving and consumer report rating for the different brands of tomato soup is negative. That was our first graph. And the association between price and sodium in a serving for different brands of vegetable soups is neither positive nor negative association. That was our middle graph. So now we are going to look at scatter plots that differ in form. So some have a linear pattern, some have a curve pattern. In statistics, the curve pattern is also known as curvilinear. So we want to match each set of measurements to a scatter plot and give brief explanations for our reasoning. So here are our 6 scatter plots, and then down below are 6 descriptions. So let's tackle this first description. X is the month number, which is January, corresponding with 1, and Y is the rainfall in inches in Napa, California. And then we're told that Napa has several months of drought each summer. So we are looking for something with low rainfall or no rainfall in the summer months. So scatterplot 3 is the best fit for that. There's higher rainfall early in the X value, so that would be January. And then it dips to no rainfall. That horizontal line is to represent 0. And then the rainfall inches increase again as we get to the end of the calendar year, November, December. So we've labeled Scatterplot 3 with the x-axis as month and the y-axis as rainfall. All right, let's match description 2. Description 2 is where x is the month number again, where January corresponds with 1, and y is the average temperature in Boston, Massachusetts. And Boston has cold winters and hot summers. So we are looking for a graph that has low temperatures, maybe even below 0 because it's measured, they're not telling us, but maybe below 0 in some of the scales, below 0 I think in Celsius, and then below 32 maybe if it's freezing in the Fahrenheit scale, and then high temperatures in the summer. So Scatterplot 5 here is our best estimate because those values start low and then increase to a peak in the middle of the x values, or in the middle months, and then the temperatures dip back down in the later months, going very cold below that 0 line in the later months, November, December. So these must be measured in Celsius if the temperatures go below 0. So we've labeled x as the month and y as the temperatures. All right, our third scenario has x representing the years since 1965 in 5-year increments. So that means each tick mark on the horizontal axis corresponds with 5 years going by. And then y is the Medicare expenditures in dollars. And then we're told Medicare costs have increased over time. In addition, the increases in costs have themselves been increasing over time. Smaller increases at first, followed by larger increases as time passed. Since the increases are not constant, we're not going to be looking for a linear shape. Since the increases are themselves increasing or growing, we're looking for an increasing curve to model these Medicare expenditures. So Scatterplot 1 looks the most like that. That's what we sometimes call an exponential growth, or like the right half of a parabola, you might say. Either type of curve it could be fit with. And so it looks like as the years increase, the costs are going up and up and up, increasing. And then the rate of increase is also changing. That's what makes the graph curve up as the increases get more and more as years go on. And so we label our x-axis as years since 1965, and then our y-axis is the Medicare costs. Okay, scenario 4. X is the average temperature in degrees Celsius, and y is the average temperature in degrees Fahrenheit each month in San Francisco. So Celsius to Fahrenheit should be a steady rate because we use a formula to convert. And so Scatterplot 2 is a match for that. We're using a linear formula. We multiply by the scaling factor and then add or subtract a constant when we're converting temperatures. So here x is the Celsius temperature on the horizontal axis, and y is the Fahrenheit temperature on the vertical axis. And see how those points would fall exactly on a line? So these are a perfect fit to a linear equation, and that's because we know the conversion from Celsius to Fahrenheit is a linear formula. Scenario 5 has x as the chest girth measured in centimeters and y as the shoulder girth for a sample of men. So loosely, I'm thinking that men with smaller shoulder girths or smaller chest girths are going to have smaller shoulder girths. And then men with larger chest girths are going to have probably larger shoulder girths. The chest girth and shoulder girth are probably roughly proportional to the height and build of the man. So I'm looking for a graph that's increasing as the chest girth increases. I expect the shoulder girth should also increase. So Scatterplot 6 here is the best match for that. So x is labeled as the chest girth and y is the shoulder girth. And it makes sense for the reasons that we said. We expect someone with a larger chest girth to also have corresponding larger shoulder girth. The girth is just a measurement around the outside. Like if you're measuring the outside of your waist, you could label that as your waist girth. So like if you take a tape measure and measure the distance around these parts of the body. Scenario 6, x is the engine displacement in liters, so that's the size of the engine, and y is the city miles per gallon for a sample of cars. And then we're told engine displacement is roughly a measurement of the size of the engine. Larger engines use more gas. So we are looking for, as the x value gets larger, as the engine displacement increases, we are looking for a scenario where the city miles per gallon are going to decrease because we're going to take more gas to run this larger engine. So Scatterplot 4 is our match for this scenario because it's got a negative association here. So we measure x as the engine liters and y as the city miles per gallon. Okay, so let's do a recap. Scatterplot 1 was an increasing curve. We said it could be modeled by an exponential curve, or you might say it looks like half of a parabola. Scatterplot 2 perfectly matched a linear equation. That was where we were converting from Celsius temperatures to Fahrenheit temperatures. Scatterplot 3 decreased and then increased, so that gave us a parabola-like shape. Scatterplot 4 shows a decrease, and it's roughly linear. There's not really a curve there. And so because we have the decrease, we say that's a negative association. As the x values go up or increase, the y values decrease. And then Scatterplot 5, the values increase, peak at the top, and then decrease. So that's also a parabola shape. We would say this is a open down or concave down parabola shape, whereas the curve in Scatterplot 3 we'd say is an open up or concave up parabola shape. And then Scatterplot 6 is roughly linear, we'd say, if we were trying to figure out if a line or a curve is a better fit. In our class, we are going to focus on linear regression, since this is an introduction to statistics. But know that in StatCrunch or other computing programs, you can also match curves, any of these curves that we've seen here, exponential or parabola. We could find an equation to match the shape as a best fit. So in a future statistics class, you might do some more modeling with curves than we'll cover in this class. We are going to mostly focus on lines of best fit, not curves of best fit.